Welcome back, ladies and gentlemen, to the second part of my series on shellcode for macOS on M1 chips. In this video, we will learn how to write a bind shell for macOS. Now, if you've clicked on this video, it stands to reason that you already know what a bind shell is, but just in case, to bring everyone on the same page, I will at first quickly review what bind shells are and how they work. In the second part, we will go through the steps of writing a macOS bind shell in assembly, while coding along and discussing each of the system calls used in the bind shell. And once we have a working bind shell, we will modify it to avoid null bytes appearing in its binary encoding. This is important because shellcode is often delivered in the form of an ASCII string, and a null byte contained in that string could cause it to be truncated before the whole shellcode is processed. So first, let's look at how bind shells work. A bind shell provides a backdoor to execute commands within a terminal for an external attacker. So that could be a security analyst, an ethical hacker, such as you yourself, my dear listener, or it could be a malicious criminal hacker with whom the likes of us have nothing to do. The machine that runs the bind shell will be referred to as the target, and it works as follows. The bind shell offers an open port for the external attacker to connect to, and it runs a shell process on the target whose input and output get redirected to the listener, to the listening port, and are thus made available to the attacker. And upon connecting to the bind shell's listener, we are able to use a shell on the target machine. So this is sketched in this picture here. Our target with a made-up IP address and our attacker connecting to this IP address, and there's a socket on the target that corresponds to this bind shell with the IP address 0000 that accepts any connection on the port 1234 that we just arbitrarily chose. And there are two problems with bind shells that I quickly want to address. Firstly, not just ourselves, the benevolent ethical hackers, can connect to a bind shell's open port, but also any malicious hacker who happens to detect that this port is open. So that is a danger. For example, imagine you're conducting a penetration test that you were hired to do in some company's network, and then some evil hacker at the same time detects that you planted a bind shell somewhere. Then that evil hacker could also exploit this backdoor and do bad things. Another problem is that if the target network is protected by a firewall, it might be that incoming ports are blocked, so that we cannot connect to the bind shell from outside the target's network. And if this is the case, we must use a reverse shell, or can at least try to use one, which, as the name suggests, goes the other way around, which lets the target connect back to our attacking machine rather than us connecting to the target. And this is more likely to work because firewalls usually only block incoming ports, but outgoing ports are fine. So a reverse shell has a greater chance of success. And reverse shells will be the topic of the third video in this series. The code that realizes the bind shell will be called the shellcode, surprisingly. And there are many ways in which the shellcode could be placed on the target machine. But this is not the topic of this video, so let me just mention them very briefly. For example, an unsecured web form might allow us to upload files to the target computer that we can somehow execute then. Or a very classical method of sending shellcode to a target is through a buffer overflow. So here, malformed input data is sent over the network to some application that causes a buffer overflow, which in turn allows us to write our shellcode to a certain part of the program's memory. And if we tweak it just right, then this shellcode will be executed instead of the original program. Now in modern days, there are a lot of protection mechanisms against this, so it is not as likely to succeed this way as it used to be, but in principle it is still a possibility. Also, shellcode can be embedded in poisoned documents and then get executed when these documents are opened by a user. And there are many other ways in which to deliver your shellcode. Many of such delivery methods require that the shellcode is embedded in an ASCII string. And in many programming languages, most notably the C language, a null byte is appended to a string to indicate the end of the string. So when writing shellcode, we wish to avoid having null bytes in our code so that our shellcode does not get truncated at the occurrence of such a null byte when the input string that contains the shellcode is processed. And once we got our bind shell up and running on the target, we can use tools such as the famous netcat in a terminal to connect to the target, to our shellcode. And our terminal on our machine will then present us with a shell on the target machine. And the command to do this is nc, IP address of the target machine and port number of our bind shell process. And netcat is by default available on macOS, at least in its BSD version. So we can use that without having to install anything else. And next we will take a look on how a bind shell is written in assembly on macOS. We will use BSD's network API, and at first I want to give you a quick summary of the general structure of a bind shell. So in the BSD networking model, a socket is an abstraction for a communication endpoint. That means it's an object from which messages are sent and received. And internally, sockets are treated by the operating system in a very similar manner to files. But for a deeper understanding of this concept, I would recommend you take a look at a textbook on the design of the BSD operating system. And please recall, as I emphasized in the first video in the series, that macOS is very strongly based on the BSD operating system. Well, once we have our socket, we wanted to be able to listen to incoming connections. So we bind this socket to a local IP address, that is a receiving IP address, and a port. And in our case, we bind it to the special IP address 0000, which means that the socket receives connections going to any device on its machine, and if they are directed to its given port number. So in our case, we will simply use the port number 1234 because it's not a common port. That means it's not associated with a very common internet service, and it's also easy to remember. So there's no deeper meaning behind this number. Next, we will simply tell our socket to listen for incoming connections on its given port. And once an incoming connection arrives, to port 1234, it is redirected to our socket, and the socket then has to accept this connection, and one connection at a time. And this creates a new socket for the now established connection. And from now on, so in the following steps, we will be using this new socket rather than the first one. And in this way, at least in principle, the old socket can be used to accept further connections while we keep working with the new socket. But in our application here, that is of no relevance. Now we want to make sure that the shell we will open on the target is accessible on our attacker's machine, on our own machine. So for this, you have to know that BSD treats sockets internally like files. And files are represented by file descriptors or socket descriptors, in the case of a socket. And on Unix systems, it is a convention that the standard input of a process has file descriptor 0, standard output has file descriptor 1, and standard error has file descriptor 2. And now we can duplicate our new socket descriptor from the previous step 3 times and assign them the numbers 0, 1, and 2. And then within the current process, all data directed to standard input, standard output, or standard error will be instead redirected to our new socket and will thus be available to the attacker's machine connected to this socket. And in the last step, we need to start the shell process. Now the standard shell for macOS is the Z shell, and its binary file is located at path/bin/zsh. And what happens internally when we execute this binary is that the process executing it will be transformed into a new process that runs the shell. And our redirected file descriptors for standard input, standard output, and standard error will be inherited by this transformed process so that the shell's input and output gets rerouted to our attacker machine. Now, this all may look like a lot of steps, but understand that the BSD networking API was designed with a much more general inter-process communication model in mind than just the internet. So it is reflected in the abstract nature of this API, and to keep things manageable, the functionality is distributed over many different functions within this API, as you can see in these many steps here. So the 6 steps we just discussed all correspond to suitable system calls in macOS. The socket system call to create a new socket is number 97. The bind system call to bind a socket to a local IP and port is number 104. The listen system call, which makes our socket listen for incoming connections, is number 106. Then when an incoming connection is detected, the accept system call number 30 can accept this connection and return the new socket descriptor for this connection. And to duplicate our socket or file descriptors, we use the dup2 system call number 90. And finally, to start the Z shell from its given binary path, we can use the execve system call, which is number 59. And please recall from the first video in the series that we can look up system call numbers in the macOS source code online, and this is the address where you can find the list of all the BSD system calls that are available in macOS. And we will look into each of these 6 steps in detail next and implement them in assembly as we go along, so that after the last step we have our fully functional macOS bind shell. First, let's look at the system call to create a socket, which is number 97. And the easiest way to find its definition is through the man pages, section 2, installed on macOS. And the man pages usually are more informative than the function declarations in the macOS source code. So let's have a look how we can find this. Here is this socket man page. We find the header file in which the function declaration here can be found. And we see there are 3 arguments: domain, type, and protocol, which I will now explain in some detail. So the first argument, domain, defines the protocol family in which the communication takes place. In our case, we use the Internet Protocol version 4, and this is designated by the constant pf_inet, where pf is for protocol family. And this constant is equal to the value 2. So 2 is the value of the first argument to our socket call. The second argument, type, describes semantic properties of the communication. For example, if the communication is connection-oriented, such as in TCP/IP, or datagram-oriented, such as in UDP. Here we choose the value sockstream, which is equal to 1, to represent the TCP protocol. And the last parameter, protocol, can simply be set to a dummy value, IP proto IP, which is equal to 0, because the first 2 parameters already determine the protocol we use completely. The return value of the socket call is a socket descriptor, and we can use this socket descriptor to receive a connection. Now let us implement this system call in assembly. So here I prepared an assembly file for our bind shell. You see I already have 6 different sections here for each system call. And recall that in ARM64 assembly, the arguments are passed in registers x0, x1, x2 up to x10. If there are any further arguments for the call, they would be passed on the stack, but we will never have that many arguments here. And the return value of a system call is stored in register x0. So this was talked about in the first part of this video series. You can look it up there. And now to implement the system call socket, we first do the following. We move the value 2 into register x0. So this corresponds to the domain argument for the system call. Then we move the value 1 into register x1. This corresponds to the type argument. And we move 0 into register x2, which is simply the value 0 for IP proto IP. And note, I don't write out the value 0 here, but I use the special 0 register on the ARM64 architecture for that. Now, I use register x16 to store the value of the system call, which is 97. Then I use the supervisor call to actually do the system call with an arbitrary input value. And recall that in the first video I said I will just use the value hex FFFF because it allows me to avoid null bytes. So here we execute the system call. And remember the return value, so our socket descriptor for the system call will be stored in the register x0. And to save this for later use, I copy it into the register x11. So this is our first system call. Next comes the bind system call, which is number 104. And we will also look that up in its man page. And here it is particularly important to provide the man page section too, because there are a lot of other programs named bind. So, for example, if I just type man bind, well, you see we get quite a confusing output. This is not what we want. We want man to bind. So here we have the bind system call. And again, we find the arguments here: socket, sock adder address, and address length. And this second argument here of type sock adder is a general structure that provides a name to address the socket. So we are using a special protocol here, the Internet Protocol, and for this protocol, this general structure sock adder can be replaced by a more specialized structure sock adder underscore in, the in standing for internet. So here I already replaced it, sock adder in. Internally, of course, this is exactly the same as sock adder. It's just a different structure declaration in the C prototypes. The first argument is a socket descriptor, and here we simply use the socket descriptor returned to us by the previous socket syscall. And the second argument, the sock adder in pointer, named address, is a 16-byte wide structure whose components we will describe in a moment. And the third argument, address length, will just be set to 16 because it's the length of this sock adder in structure, and this is a constant, so we just set this to 16, irrespective of what we fill in here. Now let's look into how the sock adder in structure is built up. And we can actually find it in the macOS source code. So let's have a look at that. And here we are again on the website with the macOS source code. So we look at the latest version and we go to the BSD part. Okay, and in order to find this sock adder in structure, we need to look at the internet components. So here net inet is the IP version 4 stuff in the BSD kernel. And the data structures are defined in in.h. And here we have the sock adder in structure. socket address internet style, as you can see here. And we see it has a few components that are, some data types that are not immediately clear to us, except for the first one, sin_leng, which is apparently an 8-bit unsigned integer, so 1 byte. But here, as a family import struct in address are not so clear. And at the end, we have sin0, an 8-byte array of characters. So 1 byte in the beginning and 8 bytes at the end, but it's not so clear how large these parts here are. Now, to find out about these other components here, we navigate to the definitions of data types in the BSD kernel. And those can be found in the directory sys, in the subdirectory _types, and here we see all these header files where these types are defined. So let's see, we need internet address, IN address here. And we see this is defined to be unsigned integer 32-bit, so it's a 4-byte data structure, simply. Then we have internet port, in port. This is a 16-bit unsigned integer, so it's 2 bytes. And then we have SA family. And this is again just 1 byte, an 8-bit unsigned integer. So this way we can find out which data types we're dealing with when we're looking at something like this sock adder_in structure. And here I have sketched it for you. The first byte sin_leng, second byte sin_family, then 2 bytes for the port, sin_port, 4 bytes for sin_address, so that corresponds to the 4 components of an IP version 4 internet address. And finally, we have 8 bytes at the end, which are just intended to pad up the size of the whole data structure to 16 bytes, because that's a requirement for the BSD socket API. Now let's look at these components. The first one, sin_length, is unused and we simply set it to 0. And interestingly, this is a point where BSD and Linux are slightly incompatible in their network API, as this element is actually missing in the Linux version of sock adder_in. So if you want to port your network code from BSD to Linux, you need to make sure to adjust your data structure by removing the lowest order byte from the sock adder_in structure. The next sin_family is the protocol family, the same as in the socket system call. So we set this one to the value 2 in our case, which is again the PF inet constant. Third component, sin_port, is obviously the port number to which we will bind our socket. And we just set this to 1234 because it's a number that's easy to remember and does not collide with any port number of a common service. And then the fourth element is sin_address, these 4 bytes, which contains the IP address that we bind our socket to. And recall that we want to use 0000 to bind our socket to every device and receive any traffic directed to the target machine on port 1234. And it is important to know that the Internet Protocol uses the big endian convention, so port numbers and IP addresses that stretch over multiple bytes have to be stored in the opposite order than we would normally store them on macOS. So keep that in mind when we implement these things in assembly. And the final piece, as I said before, sin0 is just an 8-byte padding that gives the whole sock address in structure a size of 16 bytes. And conveniently, the size of the sock address in structure matches that of a single stack entry in the ARM64 architecture, 16 bytes. So it is rather easy to build up this structure on the stack. So let's implement this now in assembly. Here we go back to our source code. So we already have the socket call, and now we implement the bind call. The first thing we do is we simply set the third argument to 16, which is the number of bytes. That is the size of our sock addr in structure. Now we use x4 as an auxiliary variable. And here we store sinlang equal to 0. So recall this variable is not used, but we have to include it in the structure. And the sin family equal to 2, which stands for the Internet Protocol. Okay, then we fill up x4 further with our port. And we use the move k instruction, move with keep, and we shift it by 16 bits into the higher positions of the x4 register. And I already converted the decimal number 1234 into the hexadecimal number 4D2. And I store it in the big endian convention here because it's used for the Internet Protocol. Now, I built up the first part, the first 8 bytes of my sock addr in structure, and the last 8 bytes will simply be 0, the padding. So I store this together with the 0 register on the stack. Recall, we can, on ARM64, we can push 2 registers at the same time to the stack. And this is the notation for decrementing the stack pointer by 16 bytes, and then storing the 2 registers x4 and x0. So here we store our sock addr in structure on the stack, and now we save the pointer. The stack pointer now points precisely to our sock addr in structure, so we save it in x1 to use as the second argument to our bind call. And I'm not setting the register x0 as the first argument, because from the first system call here, the socket call, x0 was the return value, and it contains the socket descriptor. And since we haven't changed x0 since then, it still contains this value, so we don't need to set x0 here. It still has our socket descriptor. So yeah, what we do now, we set the register x16 with the system call number 104. Which is the bind system call, and then we execute the system call with the supervisor call. Yeah, that's our bind system call in assembly. And we then call listen as system call number 106. And I'm not going to look up the arguments every time now, so you know, with the man page you can do it yourself. I'll just give you the function declaration here. So listen has the two arguments, socket and backlog, and the first one is again just the socket descriptor we obtained from our socket system call. Not much to say here. And the second argument, backlog, is the maximum number of connections we will accept. And we simply set this one to 0 to go with the system default. We implement this as well. So we move our stored socket descriptor back into x0. So here in this line we saved the socket descriptor in register x11, and now we move it back to x0. And why do we have to do that? Because in this system call here, x0 is most likely to be overwritten. So after this it no longer contains the socket descriptor, so we restore it here as a first argument. Of course, you have to check that x11 doesn't get overwritten by this previous system call here, but given that it's one of the higher up registers, that is not so likely, and practice will show that indeed it works. Then x1 gets set to 0 using again the 0 register, which means the backlog is just null. x16 is set to 106, which is the BSD system call number for the listen call, and we execute the system call. So this is probably the simplest one of the system calls. And once our socket is in a listening state, we can call the accept system call number 30 to accept any incoming connection to our chosen port 1234. And again, the first argument here is just our socket descriptor. The second argument and the third argument are a pointer to a sock adder structure to contain the address of the connection host, of the host that connects to us. But we will not use this, so we can simply set it to 0, and accordingly we can simply set the address len structure or value also to 0. Here the return value is important again, because the accept call returns a new socket descriptor for the now established connection, and from now on we will be only using this new socket descriptor. Okay, so we will no longer be using the socket descriptor from our original socket call, but from now on we will use the one that is returned by this accept system call. And let's implement this one. So again, we first have to restore our original socket descriptor. We set the address structure to 0, which means we ignore it. And the same with its length value. Now we use system call 30. For the accept system call. We execute our system call with a supervisor call. And the return value in x0 will be the new socket descriptor. So we save that one again, this time in register x12. And as I said, from now on we will only be using this new socket descriptor. Next, we want to make sure that input and output are redirected to our new socket. And to this, we use the dup2 system call number 90. The first argument, fd, is the file or socket descriptor that we wish to duplicate. So in our case, this is the socket descriptor that was just returned by the accept system call. The second argument, fd2, is the number given to the duplicated socket descriptor or file descriptor. And we use dup2 for each, the standard input, which is number 0, standard output, which is number 2, and standard error, which is, standard output is number 1 and standard error is number 2. So that way all data directed to one of these file descriptors will be directed to our socket. Can we implement this? Here we have to be a bit clever about the order. First, we move the system call number into the x16 register. So we do this once in the beginning, and then we call it 3 times. x1, the second argument, is the number that will be given to the duplicated file descriptor or socket descriptor. We begin with standard error number 2, and then we count down. And then we execute the system call. And again, we don't have to set the x0 register, the first argument, because from the previous system call here, it already contained the value of the new socket descriptor. However, after the first time calling dup2, this might not be the case anymore, so we have to restore it. And we saved it in x12 here, so we restore it from x12. Now we do the same for the next file descriptor, number 1, which is standard output. And once more, we move the saved file socket descriptor to x0. And now the register x1 still contains the value 1. So we set it to 0 for the last file descriptor, the standard input, and we can do this by using a right shift. So we right shift the register x1 by 1 bit, thus setting it to 0. And once more, we execute the dup2 system call to point the standard input to our socket descriptor. Finally, it's time to start our shell, and the system call number 59, execve, can be used to run any command with given arguments and given environment variables. The first argument, path, is the full path name of the binary file we wish to execute. So here we run the macOS standard shell, the Z shell, which is located at /bin//z/sh. The second argument is an array of pointers terminated by a null byte, and each pointer points to a C string, which is handed as a command line argument to the program that we execute, so to the Z shell in our case. Here the Z shell requires only one argument, which is its own path name, bin//z/sh once more. And we will take a closer look at how to set up the arguments in a moment. And the third argument, env-p, is an array of environment variables for the context of the program we execute, but we do not need this argument, and therefore we just set it to 0. What happens when we call execve is that the calling process is transformed into a new process running the Z shell, and it inherits the redirection of the input-output file descriptors to our connection socket. And before we implement this system call, we take a closer look at how to set up its arguments. As noted before, the second argument for the execve call, argv, is an array of pointers to the command line arguments for our shell, for the binary /bin//z/sh. Now here we have only one command line argument, which is the 0th argument, if we use the C convention to count arguments. And this is the name of the program itself, which is again /bin//z/sh. And this is a requirement of the Z shell. It's not a general requirement for the execve call. And the command line arguments are C strings, so the string /bin//z/sh must be null terminated in our assembly implementation. And also the array argv of pointers to the arguments must be null terminated. So that's something we have to be careful with, that we get all the nulls right. What we will do in our assembly implementation is that we obtain a pointer to the null terminated argument string and write this pointer into a null terminated array with one entry. And we will do this on the stack, and we will then obtain a pointer to this array of pointers by copying the stack pointer. this value is then handed to execve as the second argument, argv. So let's see an illustration of this. Here we have our stack, the stack pointer pointing to the current top entry, whose entry we don't really care about. We have our registers x0, x1, x2, which hold the arguments for the execve system call. And then we use x3 as an auxiliary register. And in the first step, we load the string /bin/zsh into the auxiliary register x3. So at this point, the string is not zero terminated, but note that this is precisely 8 bytes long, so it fits neatly into x3. And in little endian, this string becomes this hexadecimal number. So I'm just showing you that here because it will appear in the assembly implementation in a moment. So you're not too surprised by the weird numbers that will show up there. The next step, once we loaded x3, we can push it onto the stack together with the 0 register xzr. So we get this entry on the top of the stack now. And since, as I said, the string /bin/zsh is precisely 8 bytes long, it fills exactly half of the stack entry, and the 0 register neatly fills up the other half with 0 bytes, with null bytes. And the first of these null bytes in the second half of the stack entry is then the required null terminator for our path string here. So that all fits quite neatly together. At this point, the stack pointer points to the command string /bin/zsh, and we can just copy it into the x0 register to fill x0 with the path argument for execve. Okay, so we move the stack pointer to x0, and then both the stack pointer and the x0 register point to this stack entry here. And as we learned a minute ago, this path also needs to be used as the first argument for the Z shell, so the argument with index 0 in the argv array. So what we do, we simply push x0 and again the 0 register to the stack, filling the stack with this entry here. And again, the 0 register provides the terminating null byte, this time not for a string, but for the argv array, which will be the second argument to the execve call. Now, the value that's stored here is again just the address of this string here. So I didn't draw an arrow pointing here to keep the image simple. But yeah, this value here is again the same value that is stored in x0, pointing to this string. Now in the next step, number 5, we copy sp again, but this time to x1. So the register x1 now contains a pointer to our array of argument pointers. And recall, we only have one pointer. This array has only one entry. And this is the pointer argv0, which points to this string here. And the pointer to this pointer is stored in x1 now. And finally, all we need to do is set x2 to null, as we will not use environment variables for our execve call. Okay, so we implement this in assembly now. First we use x3 as our auxiliary variable, and now I directly write the value of the string for the Z shell into this register in hexadecimal. So if you do this yourself, you have to look up what the hexadecimal values of the individual characters in the string are. And this is little endian convention. And since we can only move 2 bytes at a time, we have to use the move k instruction, the move with keep instruction again. So we do this in 4 moves. Shift the first one by 16 bits. Then by 32 bits. And finally by 48 bits. And now our x3 register should contain the full string /bin/zsh. We push this to the stack. Together with the 0 register. And now we save the pointer to the argument vector in x0 by moving the stack pointer to x0. And then we store this pointer together with the 0 register again on the stack. And then we save the pointer to the argument vector in x1. Or rather, argv is the pointer to these arguments. So finally we set x2 to 0 by moving the 0 register into it. Then we move the system call number for execve into x16, which is 59. And we finally execute the system call. So at this point, we are done. We can test our bind shell now. And recall from the first video in this series the command to assemble our shellcode and to link it with the system library into an executable file. We have the AS command and the LD command with certain parameters here. So let's do that. So we assembled and linked our bind shell now, and we have the executable bind shell 0, which I will run now. So we don't see anything yet, and now I'm going to try to connect to it using netcat. So this is the command nc 10.0.0.5.1234. So this is simply the local IP address of my own machine, and 1234 is the listening port. We don't see anything happening here, but let's see if we can execute commands. Yes, we can. So indeed, we do have a shell here. It's a bit unusual because we don't see a shell prompt, but that's not a problem. We can still type commands here, as we've seen, the uname a command, which gives us information about the machine. And if I terminate the shell in this window, we see it's already terminated here as well. So we see our bind shell works. And the next thing we want to do is to rid it of null bytes. And we can use the tool objdump with its -d option to disassemble our shell and view its binary code. Let us see how that works. So we only need the object file for that, not the linked binary file. Here we get a pretty nice output where we in the first column have the byte count. So recall that every ARM64 instructions is 4 bytes wide, so we progress in steps of 4 here. Then we have the actual bytes that make up the instruction, and here we have the disassembled instructions. We can compare that with our own code, and we see, yeah, it's a pretty precise copy of what we actually wrote in our assembly program. And we already spot a few null bytes here, so that's not so nice, but we will get rid of them eventually. And to spot these null bytes more precisely, we actually combine objdump with grep. So you see all bytes appear in these 2-digit notation. So we simply pipe the output of objdump to grep 00 and see all the null bytes in our assembly code or in our assembled binary code. And we see we have 9 occurrences of null bytes. So I reproduce them here, and we will now address each of these occurrences and replace them by null byte free alternatives. So here we have the objdump output again, and the first 2 occurrences of null bytes happen to be the first two instructions in our assembly code, and we can treat them together. What we do is we replace the first move instruction, move x02, by two instructions that do not contain null bytes. First, we move the value hex 0201 into x3, and then we right shift x3 by 8 bytes and store the value in x0. That way we shift out the lower order byte 01 and end up with value 2 in x0. Now x0 contains the value 2, and we can now right shift the value 2 in x0 by 1 bit to move the value 1 into the register x1. And in this way we can replace those two instructions by 3 other instructions that do not contain null bytes. So let's implement this. Here our first two instructions are the ones we have to change. So first we move hex 0201 into x3, and then we right shift x3 into x1 by 8 bits. And then to get the correct value into x1, we right shift x1 by 1 bit into, we right shift x0 by 1 bit into register x1. And we can assemble that now. You see now I'm using the file name bind shell without the index 0, so this is our final, or will eventually become our final bind shell. We create an object file and dump the disassembly again. Grab the 0 bytes. And we see that indeed we have removed 2 occurrences of null bytes, so there are only 7 more occurrences left. Now we look at these 2 move instructions. So those are move instructions where we have an immediate value being moved into a register. And we can do something similar here. We use, again, shifts to avoid the null bytes. So instead of moving the value 2 directly into x1, we move the value hex 0201 into x1 and then shift it right by 8 bits and end up with value 2 in x1. And similarly, we replace move x1 1 by moving the value 0101 into x1 and then again right shifting by 8 bits. And these were down here. We replace this one. Instead of moving 2 into the register, we move the value hex 0201 and then do a right shift by 8 bits and end up with the correct value. And the other one was here. And another right shift by 8 bits moves the value 1 into x1. And we see again we have reduced the number of null bytes by 2 occurrences. So all occurrences that are left now are move instructions where we move from one register to another. First we handle these 2 where the stack pointer is not involved. So this one and this one can be replaced by trivial shifts. That is, instead of moving x0 to x11 or x12 respectively, we simply shift x0 into x11 by 0 bits. So we're not doing anything other than moving it here, but we use a different instruction for that. And luckily, these shifts do not require any null bytes in the encoding. The first replacement is here, where we save x0 for the first time. And this becomes a shift. Doesn't really matter whether left or right shift, just has to be by 0 bits. And the next one is here, where we save x0 in x12. And again, we assemble it, check the output, and we're left with 3 null byte occurrences. And these all involve moving the stack pointer to one of the other registers. And now the thing is that an operation such as this trivial shift does not work when one of the registers involved is the stack pointer, or rather if the second argument is the stack pointer. This is simply not allowed by the ARM architecture. So we cannot do this. We need to use a different trick. So these are our remaining null byte instructions, but we can all deal with them in the same way. We do a mock addition by 0, and if we add 0 to a register, we don't actually have to give the value 0 as an argument, but we can just use the 0 register, and in that way we can avoid having null bytes in the encoding. That is a pretty neat feature of this 0 register on the ARM architecture. So we implement this. Now, where do we have those? One is here. And then we had 2 moves with the 0 register down here. We assemble, we do the object dump, and indeed we do not get any more null bytes in our code now. Now, what remains to do is to confirm that the shellcode still works, even with the null bytes removed. So we have to link it again. We run the bind shell and we use netcat again. And indeed, the shell still works. We can execute commands in netcat. And when we terminate the shell, netcat also terminates. So we are done. We have created a null byte free bind shell and confirmed that it still works. That makes us happy. So I'm at the end of this video now, and if you watched the video up to this point, it seems reasonable to assume that you are interested in its subject. Therefore, it would also seem reasonable for you to like this video and subscribe to my channel so that you can be exposed to more interesting content in the future. Go, do it! Don't hesitate and tell all your friends to do the same. They will be very grateful to you. In the next part of the series, we will see how to write a reverse shell for macOS on M1 chips. And thank you very much for watching.